Good day to you all and welcome to Forensic Bites. Today we're going to be talking about instrumental methods in forensic science, particularly focusing on basic functions of mass spectrometry. What we're going to cover are the types of instruments that you might encounter in a forensic laboratory, the kinds of experiments that can be run on those different calibers of instrumentation, how discriminating the data from those experiments are for a suspected illicit drug sample, some simple data interpretation, and an example of a database where you can find reference information to correlate with your unknown substance. So mass spectrometers are considered to be one of the most discriminating types of instrumental technique used in forensic science. I've pulled this table out from the journal shown down here, and it ranks the top 4 instrumental techniques in terms of what is the most discriminatory technique. Now, here discriminatory basically means how well can your technique separate or identify the differences between two closely related chemical species. 4 techniques ranked are mass spectrometry, infrared spectroscopy, Raman spectroscopy, and X-ray diffractometry. These 4 are ranked as either 5 stars or 4 stars. And if we look at mass spectrometry, focusing there, we can see that it can identify chemical substances. It's also claimed that it can quantify the amount of the substance there, although I would say that more often than not, it'll have some sort of linked instrument to allow it to do that. So very often a mass spectrometer is the end point linked to a gas chromatograph or a liquid chromatograph, and it's those chromatographs that actually quantify the amount of each component of your sample, and then the mass spectrometer's job is to identify unambiguously what the structure of that chemical species is. Now, all 4 of these techniques are lab-based. The cost is listed, which for mass spectrometers is varying between $5,000 which seems incredibly cheap to me. That must be for a very old, low-resolution instrument, doubtlessly second-hand, all the way up to about $200,000 for a new, advanced model. You might even pay more than that for a tandem mass spec type instrument, which would have, modern detection methods like an Orbitrap and these types of things. In terms of ease of use, it's intermediate to advanced, so you probably need some chemistry training or at least analytical training if you're going to know how to prepare the samples, prepare the instrument, and then interpret the mass spectrum at the end, although the time of the analysis is measured in minutes, which is good. So think about some of the other 5-star methods listed there between infrared and Raman spectroscopy. These are listed as 5-star, although I'd probably give those a bit of a caveat. If you have a very pure sample that you're analysing, sure, infrared and Raman, they will give you very, very clear spectra of products which you can match to known samples. But when you start looking at mixtures, it becomes much more complicated to use those 2 methods because they often will not have an inbuilt means of purifying your sample. So unless you're really, keen on doing some purification beforehand, infrared and Raman are both challenging, shall we say, in terms of discrimination to the same level as a mass spectrometer. Last one's kind of interesting. So X-ray diffractometry, I would argue if we're talking about single crystal X-ray diffractometry, that is the best, most discriminatory technique out there because that will literally give you a model of your unknown sample. Now, it does have a fairly large limitation in that it can only analyse crystalline samples, but that said, it is probably the most unambiguous of all 4 of those techniques in terms of telling you what your sample is. Now, what I suspect is that they are actually thinking more about powder X-ray diffractometry, and as a diffraction method, indeed, that would be ranked probably 4 stars. So it gives you a very similar output to an infrared or a Raman instrument in that it will have a spectrum with a whole bunch of peaks in it, and you can just do sort of a kind of a fingerprint analysis matching your unknown to a reference sample from the database, and you can match that way. Second downside, I guess, of X-ray diffractometry would be the cost, because those instruments are extremely expensive. Now, despite mass spectrometry being arguably the most discerning or discriminatory of techniques, not all mass spectrometers are made equal. There is a wide scope of sophistication or variability in sophistication for mass spectrometers when comparing low-resolution older instruments with high-resolution or tandem instruments that are very modern. So the older low-resolution instruments are far less discriminating than the brand new ones, and we're going to cover a few of the general classes of mass spectrometer here, focusing on the kinds of outputs they're going to give you when you're doing your analysis. So to focus initially on the low-resolution instruments, initially, like thinking about their history, they were only suited to small molecule analysis. These were done with electron impact as a detection method initially, and then later on came electrospray ionization and MALDI in the late 80s. So those two techniques opened up mass spectrometry to large molecules, so it became more relevant for fields like toxicology, where you're looking at biomolecules and their metabolites. But these early instruments would typically have only single quadrupoles, so that's the means whereby charged ions are separated from one another, and ion traps, which are sort of the first basic detector that we used in mass spec instruments. And the combination of those two things gives them a limitation on the amount of resolution that they can provide. They may have no decimal points in their answer, or they can have regularly up to 2 decimal points for a modern low-resolution mass spec instrument. Looking at the diagrams, so the diagram on the left, that is the ion trap as you would recognise it if you took it out of an instrument, and the diagram on the right, that's just showing how the charged ions become trapped in the centre and then they become siphoned off, typically according to their charge. So this is sort of the detection method of these earlier instruments. For the high-resolution instruments, these are obtained from having, I guess, different components, more modern components within them. So they might have a time of flight or an Orbitrap detection method within them. So they're shown in the diagrams. And this imparts far greater mass resolving power. The increased ability to discern mass of a charged ion allows the molecular formula to be discerned. You can see the isotopic ratios within these fragments. And for a really, really powerful bespoke instrument, you might even see the extremely fine isotopic structure of individual isotopic peaks. So just to talk about that a little bit, we've got a diagram shown here, and it's essentially each of these coloured traces is showing how a molecular fragment, so it's the same molecular fragment looking at all of them, would appear based on the quality or the resolving power of the instrument looking at it. So for an extremely basic instrument with a very, very low resolving power, all you might see is the average mass of all the isotopes lumped together. So that is the red trace shown there. Now, as the resolving power sort of increases from about 1,000 maybe up to 10,000, this average mass is going to resolve into the monoisotopic masses. So you start to see the individual isotopes, provided those isotopes are in a relatively high abundance. So for most mass to charge fragments, or molecular fragments, I should say, it will break down into something that looks like this, and these are going to be the different isotopic forms of carbon, which are in relatively high abundance. Similarly, if you had something like the halogens, so bromine is a good example. Bromine has 2 isotopes that are approximately in 50-50 percentage abundance. So you would start to see a 1-to-1 dimer resolving if you had a bromine atom within it. As we keep going up into more and more advanced instrumentation, so with a resolving power of around about 50,000, this broad lumping of isotopes becomes really, really sharp isotopic peaks. And this is where you can start to get many, many decimal places on the end of your mass to charge ratio. So, we're looking in around about the range of, 774, 775. So if we were looking at this peak here, you might be able to discern that it is, mass to charge ratio of 0.01265 Dalton. So you get all of those additional decimal points, and we're going to talk a little bit later about what those decimal points can actually tell you about the nature of the chemical species that you're trying to detect. And so as we go to what I would say is nearly theoretical resolving powers, so up to about 1 million, I don't know if these instruments actually exist. If they do, it would be in a very high-tech, fancy, probably non-forensic laboratory, so more of a research laboratory. And if we look at one of these very, very small isotopic peaks, we can actually see that peak breaking down into the fine isotope structure. So where initially it might have been breaking down only according to the different carbon isotopes within it, now you're also getting the splitting from, say, the very, very small amounts of hydrogen isotopes and nitrogen isotopes and all of the other elemental isotopes that you may not typically see in your mass spectrum. So in terms of applying this technique to forensic analysis, while mass spectrometry, I guess, as a whole is one of the most discriminatory techniques for figuring out what a chemical unknown is, for forensic science, you really require a high-resolution instrument. These lower resolution instruments can't distinguish between chemical species of similar mass or even identical mass if you're only looking at it at low resolution, be they licit or illicit substances. Just to give you an example of that, we're going to look at some spectra of relatively low resolution instruments, looking at this methamphetamine derivative shown here. So the chemical formula of this methamphetamine derivative is C11H18N+. It's protonated, so this is probably after an electrospray experiment because it actually has that proton included. And we can see that the predicted mass to charge ratio that we're looking for this cationic fragment is 164.14337. And that is the 100%, so that's the largest peak that you would see. And then down here we can see this 11% lower abundance peak at 1 Dalton higher. Now, given we're only looking with a low resolution instrument, we don't have any decimal places, so all we're seeing is a fragment with a mass to charge, of 164. And that really does match with the mass to charge that we expect for our methamphetamine derivative. So far, so good. But the downside to these lower resolution instruments is that because we don't have any of the decimal points that allow us to sort of focus in on the chemical formula that we're looking at, there's plenty of other chemical species out there that will also have a mass to charge ratio of 164. So I've drawn another one here. This is 4-amylaniline. As we can see, it actually has the same chemical formula as our methamphetamine derivative, so it also has a mass to charge ratio of 164. It's not an illicit substance, as far as I know. Here's one that has a different chemical formula. So this is an indolene carboxylic acid derivative shown here. It's still cationically charged, despite the chemical formula being quite different. So C9H10 NO2+, it is still going to have a mass to charge ratio of 164. So this one still fulfills our requirements according to what the instrumental output is. And I quickly checked the database before. There are 157 other candidates in my database of molecular species that will give you a mass charge ratio of 164 in the positive spectrum. So how do we know what's the true structure of our fragment? We need to be sure because obviously, if there's 157 other candidates, that's quite a lot of doubt that can be raised in the mind of a jury later on. So one way around that, if we are sticking with a low resolution instrument, so this is doubtless a more modern low resolution mass spectrometer, we have 2 decimal places to work with. That's still not enough to unambiguously figure out what a molecular formula is, but this time we're looking at codeine and it has a fragmentation pattern shown here. Now, our molecular ion peak, which is the last one shown here, it is a match for this cationic fragment of codeine, so far so good. But what's interesting is, as part of the initial treatment that you apply to your sample when you inject it into the mass spectrometer, it essentially gets showered with energy. So basically, to form ions, it absorbs quite a lot of sort of either electrons or charged particles, something to give it that ionic form that's needed to pass through the instrument. And in doing that, the molecule absorbs quite a lot of energy. Sometimes it can just sustain that energy and it comes out the end as the molecular ion, but sometimes that energy is enough to trigger a fragmentation process in the molecule. And if that occurs, the molecule loses parts of its chemical structure, which means that it has a different mass, giving it a different mass to charge ratio, and you'll also see these fragments come out the end in your spectrum at the end. And the way that a molecule fragments is relatively unique to that molecule. So despite earlier I showed you 157 variants that will have, a combination of atoms that gives you, 164, the way that each of these different molecules fragments will be unique. So we can take advantage of that, and instead of just focusing on the molecular ion, we can also look at the fragmentation pattern and where these fragments actually appear. And as you gain more experience with mass spectrometry, you'll also come to realise that there is a logic to how these molecules fragment. So one thing about chemical structures that you probably know is that these aromatic rings, so these rings of carbon shown here, they're very, very robust or strong. They don't break apart easily. And if we have a look at each of these fragments that are assigned, we have this same ring of carbon present here. And that begs the question, so what are the weak points in our chemical structure? So where is fragmentation probably going to occur? And usually this fragmentation process occurs to either side of a heteroatom. So something like oxygen or nitrogen, these are magnets for the energy that is being applied by the mass spectrometer. So that's where it sort of congregates. And so bonds leading into oxygens or nitrogens, these become weak and points where it can break apart. And if we have a look, so if we compare this molecular ion to the first fragment, one of the points of fragmentation we can see is between this aromatic ring and the methoxy group shown here on the end. So this is the point where the fragmentation has occurred. I think it fragments in other areas as well, but that's the one we're going to focus on. Going a little bit further, we can see that here we have a nitrogen group shown here. That is one of the fragmentation points here, whereby this entire group flies off the molecule. We also note that there is a fragmentation point between the methyl group and the oxygen shown here. And again, going from here to here, we can see that there's a fragmentation point between, again, this carbon ring and this methoxy group. So that group has come off as well. So the more you do mass spectrometry, the more you come to realise that there are fragmentation patterns that are just primed to occur. And as you look at your molecule, you can start to say, okay, we're probably going to lose fragments of methoxy groups are going to come off, and maybe this nitrogen group is going to come off. And that's how these assignments are effectively done. But even if you don't have that understanding, if you have a relatively complex fragmentation pattern, again, you can use that in sort of a fingerprint type analysis, whereby you will have a reference spectrum for a known sample of codeine. You will then be able to check, okay, I'm expecting a molecular ion here, this fragment at 281, a fragment at 266, and a fragment at 249. And if this is then our unknown, we can tick off each of those fragments and say with a relatively high degree of certainty that yes, indeed, our unknown sample contained codeine. So moving on to accurate mass or high resolution mass spectrometry, here you can see the number of decimal points that we have to play with at the end of our fragmentation ions has increased greatly. So we've gone from 2 decimal places up to 5 decimal places. And when we have this degree of accuracy in terms of measuring our mass to charge species or our fragments, one thing we can actually do is we can match these mass to charge ratios to what we expect for a specific chemical formula. So now we can't really change around the different numbers or types of atoms that we see and, give a recombinant number of 394. If we change this chemical formula, it's going to change the decimal points enough that we will notice. And we can say, based on the mass to charge ratio that we see in the spectrum, that it is not a match for that combination of atoms. It is only a match for a chemical formula of C24H32N3O2+. Now, you might be looking at that and saying, hang on, that combination of decimal points doesn't actually match our expected combination for this structure shown here. And that's true. It's very, very unusual that you will get a perfect match between what you're expecting to see and what you calculate you will see. But the degree of error should be small enough that you can still make a match between the two. One of the things you typically would do is you would take a known standard and you would run it through the accurate mass spectrometer, and you would just see how well the mass spectrometer assigns your standard compared to what you expect to see. And if it is matching to the standard within your degree of error, you're going to say, okay, that's fine, and then you'll run your unknown sample. But some degree of variation between these two numbers is acceptable in terms of still making a match to a specific chemical formula. Now, one thing to say is that despite matching your specific chemical formula shown here, you can still have different combinations of the way those atoms are put together and still retain an identical chemical formula. So on the left, I've shown the structure of tetrahydrocannabinol, and on the right, I've just made up my own chemical structural species. It doesn't break any of the rules of chemistry, so, theoretically, this molecule could be made for all I know. But the point is that the chemical formula between these two species is identical, despite the structure being different. So this compound here, this is an illicit substance. As far as I know, this compound here is illicit. There's nothing illegal about that substance. And yet when we predict what the mass to charge ratio we should see for the molecular ion is, it's identical between the two because they have the same chemical formula. So just because you get a matching molecular ion that matches the chemical formula, you can't make that deductive leap to then say, oh, it must be this LSD molecule, because it could be something that just happens to have an identical chemical formula, as unlikely as that might be. But again, even though, what we have in addition to that is we have the fragmentation pattern. So if you can say, okay, it is the correct molecular formula and the fragmentation pattern actually matches what we expect for LSD, then you can make a definitive assignment that indeed it is the correct structure, the one that I think it is. Last thing I wanted to talk about was tandem mass spectrometry instruments, or tandem MS fragmentation analysis. So one thing we've been saying is that this fragmentation pattern is really important for unambiguously assigning an unknown chemical species, so matching it to, say, a known illicit substance in a database. What might happen, though, is you might not have that many fragments to work with. So here we have, basically, we could be looking at morphinone or codenone, depending on what this functional group is. Let's just look at the top one. We're going to look at morphinone. So if you ran morphinone through a mass spectrometer, what you're going to get is this molecular ion peak. So the top one shown here, you will get 1, 2, 3, 4, 5, 6 fragments in your spectrum. But one thing that we can do with a tandem mass spectrometer is we can actually tell the mass spectrometer to capture and collect this fragment. So it will start storing this fragment, and then it can subject that fragment to another round of mass spectrometry. So it bombards this fragment with additional energy. That causes more fragmentation, and then you get additional peaks that are derived from one of the fragments. And you can actually pick which fragment you want to collect and do this. It wouldn't be very intelligent to choose one of these smaller fragments because they can't really fragment more than they're going to. So usually you'll choose a relatively large, complex fragment that can undergo further fragmentation. And so based on this fragment, you can get an additional 1, 2, 3, 4, 5 fragments. So basically your experiment's gone from 1, 2, 3, 4, 5, 6 fragments total to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 fragments total. So it just makes your fragmentation patterns more detailed, and provided you can do this experiment on a known standard of your suspected illicit drug under the same conditions, you will be able to replicate these and match them all together. And that will allow you to assign unambiguously what your unknown structure may be. So the final thing I wanted to talk about is where can you find databases of mass spectra? So known substances that you can compare in a sort of a fingerprint way to say whether or not my unknown fragmenting sample is a match for a known, already run illicit substance that has been unambiguously assigned. And any forensic laboratory is going to subscribe to a database that contains all the common illicit drugs and their mass spectra, as well as a whole host of other spectra as well. So, infrared spectra, Raman spectra. Basically, if it's been run, it will be in the database. There will be SOPs, so standard operating procedures, listed for generating that spectra. So, the setup for how you set up your mass spectrometer, things like the cone voltage, the solvent that you would use, the concentration, all of those sort of details that you need to make up your sample. You would replicate those to have the best chance to replicate the known spectrum that you're trying to make a comparison to. And if you do that, part of the function of the software on a mass spectrometer is to do sort of automatic searching and matching. So it might say after you've finished your experiment that your unknown matches the known sample for morphine with a 99.9% degree of overlap. And a great example to look at some of these searchable databases is the NIST Chemistry Webbook. And I've shown the web address down there, but just to show you what it looks like, if you follow that web address, you come up to a page like this, where you can search for chemical species as well as the type of data that you want to see for it. So here I've input morphine and I want to see a mass spectrum from morphine. If you click on search, you'll come up with something like this, where it gives you the molecular ion and the fragmentation pattern that you are liable to see if you were to run morphine afterwards. So to conclude, this is only a really very basic overview of how mass spectrometry is utilized in forensic science. I haven't covered anything involved with the combined instrumental techniques like GCMS, so gas chromatography mass spectrometry, LCMS, liquid chromatography mass spectrometry. These are ubiquitous to forensic science. It's very rare, I would say, that you have a mass spec sitting alone by itself, all lonely on the bench. Usually you're going to have other instruments that can do purification that lead into the mass spectrometer and then do the assignment of what the unknown chemical species are. I also haven't covered at all the very technical aspects of how mass spectrometers actually work, and I'm likely not even qualified to do that. But thanks for listening. That's all I have to really say about today. Feel free to tune in later when we have more content.